Recorded is rolling. It is Wednesday, February 5th. I have a lab for you guys today. Foxboat Buoyancy Lab. You guys have this lab page on your desk. So walk through that with you guys. Some other things. You guys know AP. Oh my God. It's AP night coming up Thursday the 13th. It's about a week from now. If you want to present, make a pitch to younger students, considering AP program, tell them what AP is about, then go see Mr. Dravies and he'll set you up on AP night. The way we're organizing this, I think it's by department, so had a few students, maybe one for each department at least, that would be pretty good. All right. AP Classroom, Unit 8, which is this fluids section. This has been open a while. Let's have that due on Monday. Here's what we're going to finish this week. So today's Wednesday. Have you guys do this lab. Hope you guys have a bit here. Okay. Then Thursday, Friday, we're just going to solve textbook puzzles in class. Right. So by the time the weekend rolls around, I think you guys will see everything and try to figure stuff out. Okay. Also, today's the last day I'm taking rotational dynamics quiz. So almost everybody turned that in over 2 weeks ago. Just double check, make sure it's in. Yeah.
Can I get a spare one? I lost mine.
Yeah, just a minute here. All right. And then here's how you guys did on simple harmonic motion quiz. Well, here's top scientist anyway. And so awesome job. You made either one of those lists for top scientist, simple harmonic motion. Way to go. All right. So I go back to yesterday's agenda. I was telling you guys the main idea is like if you want a quick checklist for this fluid section is right, Archimedes principle, which is really going to be applicable today. Okay. Now, right, there's also, well, let's see if I can dig these posters up real fast. Okay. Pascal's principle, right, also has to do with pressure. So for Archimedes, and it says how much pressure there is, or actually it has to do with buoyant force, is what it is, right? Pascal's principle is looking at pressures at different fluid depths. Okay. And then if you have fluid in motion, say water flowing through a pipe system, flow is conserved, and the Bernoulli's principle has something to do with pressures, which I haven't really gone into a lot of detail. I just introduced that poster yesterday, but I'll solve some puzzles with you guys with these middle two tomorrow. Okay. But all right, what do we got here on this front? So some posters here. Right. Well, here. Start with Pascal's principle. So Pascal's principle says fluid pressure is transmitted undiminished. Pressure is transmitted and diminished within a fluid. Okay, so the pressure on the left side, pressure on the right side. Okay. Now, how much pressure is there? Ooh, guys, here's a good pressure formula. Do you guys think the deeper you go, the more the pressure? Okay. Do you think it scales up linearly? If you're twice as deep, do you think it's twice the pressure? Yeah, that's exactly what this is right here. So the pressure is equal to the density of the fluid that you're going down to. So water most of the time. Okay. Gravity field of the planet and how deep you go. Okay. And then the resulting force, guys, buoyant force wants to push you which way? Down or up? Aha. Right. So if you have an iceberg floating here, then it's an equilibrium balance between the weight pulling down and the buoyant force pushing up. This one's going to be really handy today. Okay? Actually, that's what Archimedes' principle is. Okay. Do you guys see this formula? And this formula, the same formula, right? Okay. Same thing. So I guess Paul Hughes did this yesterday, where he took a weight that weighed so many newtons. He dunked it in the water, and the weight reading went down. Okay. Now Earth is still pulling on it just as much as it was before, but the tension of the string decreased, and the difference is the buoyant force, which is exactly equal to the weight of the water displaced. Okay, so you can take this, you can break it down a little bit further. You say, well, I know weight is mass times gravity field, and we've been writing weight as mg pretty much all year. Okay, and what is mass? No, this is mass of the water displaced, right? Times g, right? So the weight of the water displaced. Well, that's density times volume. And the density is the density of the fluid. Guys, see if you guys are following. What density is this right here? Is this the density of the weight or the density of the water? Density of the water. Whatever fluid's in. Okay. And this volume is the displaced volume. Now, if the object is completely submerged, then that would also be its own volume. But if it's like this iceberg float here, then it's only the part that's pushing water out of the way. Okay. Do that. Okay. Oh, yeah.
For the Pascal example, where was the weight measured? Is it the difference between H2 and
H1? Here, I'll show it with this one. So here's all right, so we got a Pascal question, like how much pressure is there? Okay. The deeper you go, the more the pressure. So it's rho GH. Rho is density of the fluid. G gravity field. H is like how deep you go, right? Like a height chain, right? Okay. So this is a really classic setup. I remember seeing this all over at college, and then AP asked you guys some questions about this too. Okay. So do you guys agree that like down here the pressure has to be the same all along this level? Yeah, it's all the same, right? Maybe have different fluids. Maybe have guys, which fluid is the most dense on this poster? Which is the most dense? Yeah, this blue one, right? This blue one's the most dense, right? Which one do you think is the second most dense? Probably this gray one here. I think that'd be fairly dense. And then this green and this yellow would be maybe like oils that are fairly light, right? Because there's not a whole lot of gray that's pushing this down that has to hold up all this over here. I think probably the green is the third most, and then this yellow is the least dense of the four fluids. Guess that, right? Right. So if the pressure is equal down here, right? Now I go back to this Pascal one. I did type here equal pressures at equal depths, but that's only true if it's the same fluid. I need to go back and amend this a little bit because I try to simplify and blah blah. But it's really only true if it's the same fluid, and also if it's not in motion. If it's in motion, then Bernoulli kick in and pressures can change too. Right? So if it's stagnant in the same fluid, so that would also be true right here, isn't it? Because isn't this line the equal pressure, right? Right. Now above that, well, we got different kinds of fluids, so you got to be careful. Right. But what I can say is that let's say I take this point right here. Right. The pressure is equal to, well, there's some atmosphere pushing from above. You guys see how I have both ends open to the atmosphere? Right. Now there's a twist on that too. Sometimes that's not always the case, right? But here, just have a YouTube right. So I got the atmosphere pushing down on both sides, right? And then the rho GH from this gray and the rho GH from, well, this little bit here, brings you up to the pressure here. And then how about on the right side? We got the atmosphere pushing down, and then the rho GH from this gold, and then this rho GH from this green, right? And then if you want to go down to here, you can just add the rho GH naught of this blue, right? It's equal on both sides. That's exactly what this equation says. So on the left side, I got the pressure from the atmosphere, this rho GH naught, this rho GH1, and this rho GH2, right? And then on the right side, I got the pressure from the atmosphere, this rho GH naught, rho GH3, this rho GH4, right? And they have to be equal to get down. Yeah.
And when pulls push up greater than the other things pulling down.
All right. Yeah. I'll get right to that. Yeah. All right. All right. So are you guys good with this so far? And you guys see what cancels out on both sides? Right. If both sides are open to the atmosphere, that would cancel. Right. Although careful, because sometimes there's a twist question. They have like one side capped, or I think one question they have like or there's variations on this. Right. Might not always cancel if one side's sealed or something. And then this rho GH naught is the same on both sides too. Right. So it kind of boils down a little bit. Here's it. All right. So let's go back to Archimedes' principle right here, or this one if you like. Right. So can the buoyant force ever be more than the weight? Well, if you took a ping pong ball and you forced the ping pong ball down below the water, right? The ping pong ball weighs a little bit. And do you think the buoyant force would be more than the weight? Yeah. And you let it go, and there's a net force up, so it accelerates up. Zoop. Right. Now, if it's just floating there at rest, guys, what do you know for equilibrium? What's the net force equal to? Zero. Right. Which you guys are going to see today. So doesn't the buoyant force have to cancel out? Right. Now remember, the buoyant force is only caused by the part that's submerged, pushing water out of the way. Right. And the weight's caused by the entire mass, the entire weight. Okay. Okay. Right. Okay. Yes, it's that answer.
Yeah. Wait. So if it's that. So no matter how high up it's floating, it's just assuming that force is zero. It's sitting there.
Yeah, guys. Anything at rest is equilibrium. In equilibrium, net force is always zero. Right. That's your framework for equilibrium. Yeah.
Is it possible to get something that neither floats nor drowns, just sort of frozen in the water in a static position?
Yeah, guys, if you saw let's say you saw a submarine, it was just kind of floating along and it wasn't really rising or falling. What could you say about the density collectively of that entire submarine? Same density as the surrounding water. Yeah, if it's the same density, then it'd be no different, right? Okay. Right. All right. Guys good there? Okay. All right, let's take a look at this lab. I want to get you guys started so you what looking at. So you guys have these aluminum squares on your desk. If you need more, let me know. I put at least a couple on each desk. You guys have a tub of water. Like I said. Now, what I'm gonna have you guys do is fold these into little box boats. Here, I got a model down here. You see, you can pull up the edges around, make a little box boat. Right. Okay. And if you fold one and you want to refold it, then what's nice about this aluminum foil is, of course, you can unfold it and refold it like you want. Okay. Also measure how much you're folding up each side as you get. So what I might do is make creases all the way around, like this. Okay. Stand at the sides, stand at the side. Okay. Pull these corners a little bit.
No, we should do a group project. And we get the water.
Okay. Boom. Got a little box boat. Okay, maybe make that a little prettier right there. Okay. All right. So you guys see a nice little box boat there, and then you guys have some lab weights on your. Oh yeah, go ahead. You don't have a what? Okay, yeah, guys, I put 2 aluminum squares on each desk pod. I can get you guys more if you need more here in a minute. Okay. Then you guys got some lab weights. Can you guys protect the lab weights in here if you want to? Like this? Okay. And then, of course, it's gonna be in the water, so it'd be like floating, right? But if you put too much lab weight, I bet at some point it's gonna sink down to the water, right? Right. Hey guys, these lab weights, the number stamped on them, guys, this number has what unit attached to it. This is so many what? Grams. Okay. Now, guys, be careful today. I got grams here. It might be convenient to measure in centimeters, but if you're measuring force in newtons, guys, force in newtons breaks down into what? Kilogram meter per second squared, right? So, can you guys be careful about units today? Grams per guys, how many grams are in a kilogram?
1,000.
1,000. How many centimeters are in a meter? 100. Okay, so can you ask? Right. So what we got here? Gold designed a box boat with aluminum material, so basically the aluminum square, to maximize the weight that the boat can carry. Ooh, suppose you're trying to build a little box boat, you want to put a bunch of cargo in it and take this across the lake. Okay. Okay. You want to maximize the cargo. Okay. All right, so draw a free body diagram for the floating boat. Guys, what 2 forces are acting on this boat?
Buoyancy and weight.
There you go. So the weight pulls down, the buoyancy holds it up. Right. I think I bet it's this one right here pretty much, right? About like that. Okay, buoyant force equals what times what times what? Here, I got it right here.
Density of the fluid.
All right, so everybody's got that answer right there? You guys got that? Buoyant force is, guys, what does this stand for? Yeah, rho is the density of the water, right? You guys know what the density of water is?
Yeah.
Okay, here, I'll give you guys 2 values. You can call it 1 gram per cubic centimeter. So if you have a little cubic centimeter about this big right here, okay, that'd be 1 gram. Okay. Or how about, guys, how many kilograms in a cubic meter? Here, guys, imagine this. Guys, when I say cubic meter, here's 1 meter. What if you have 1 meter wide, 1 meter deep, 1 meter tall? You guys see a big old box, I filled that with water. How many kilograms is that?
A lot.
1,000. Yeah, guys, that's 1,000 kilograms. Okay. So that could be helpful. Here you go. I just gave you guys these 2 answers right here. Okay. Here's the density of water. I just gave you the 2 numbers for those 2 different perspectives. Gram per cubic centimeter and kilogram per cubic meter. Okay. Gravity field. Guys, what's the gravity field on Earth? What do you want to use? Okay, 9.8 meters per second squared. Okay. Now, if you somehow got on the track of centimeters, how many centimeters per second squared is that? About 980. Right. Okay. Right. All right. Now, if you look at this model, then do you guys see the more you fold up a side, it'll make the box taller, right? But what happens to the square base on the inside? It gets what? It gets smaller. You guys see a trade-off? Right? Like if you started just with a flat sheet of aluminum, that's not going to carry anything, right? I can put this on a flat sheet, it's going to immediately sink. Okay. So I started to build up the sides a little bit. Okay. And then now I can carry some cargo. I say, hey, what if I want to carry more cargo? So I build the sides a little bit more. Okay. Guys, if I keep building up the sides, like if this is 12 by 12, that's what it is. It's 12 centimeters by 12 centimeters, right? How much can I fold up the side before I can't fold it up anymore? 6. Yeah. Because guys, once you hit 6, you're just folding the thing in half, aren't you? Right, here's folding each side of 6. Right, does that have any volume anymore? No. This would definitely just sink, wouldn't it? Right. So you guys see like a domain restriction, how much you can fold up X, right? Right. Does everybody get that? Because if you get that, I think you can figure out this equation. What is Y in terms of X? Y is, well, one side of the base of the box. and X is how much you fold up each side. There's its own constraint equation here. Right, an expression for the volume in terms of X and Y. Now guys, this one's supposed to be real straightforward. This what's the volume of a box? Length with height, right? Length with height. Right? And it looks like the length and the width are the same. They're both just Y, get that? And the height's gonna be X. Right? Can you multiply that together to make an expression in terms of both X and Y? You guys get that? Right? It would just be Y squared times X, right? Okay. Now, the next question. Combine these two expressions to come up with a volume of the box only in terms of X. Ooh, right? Because this one, I think you guys just wrote Y squared times X, right? Or some version of that, right? Here, X is Y squared. But Y and X are related to each other, and that's this formula up here. I want you guys to come up with. The more you increase X, Y gets less and less. Isn't that true? Do you think you can take this, whatever equation you come up with here, substitute out Y in this equation, and come up with volume strictly in terms of X, how much you fold up a side? You can do that, right? Complete this table. So values for X and Y. Okay. What would the corresponding volume be? Which you can use the formula for, right? And what would be the maximum buoyant force? So like suppose you load it up with weights and it sinks down just to the brim, right? So it's just floating, right? Just barely floating, right? How much buoyant force, right? No, again, there's going to be a trade-off. Like, at first, when you start to build up the sides, suppose you're like 0.5 centimeter or 1 centimeter for X, right? You go more and more, right? You can put more and more and more weight in that box boat, right? But at some point, it's going to get too skinny. In fact, with this, the volume collapses to 0, so that's like way past the optimal point. But this is an optimization type lab, right? So you get more reasonable looking boat going again. But more, it's my original boat, more like this, right? The aluminum, you can unfold it, refold it, right? That's better looking box boat, right? Okay, right, you guys good so far? Good so far? All right. Now, a couple graphs. So what is Y as a function of X, which you have an equation for by this point, or well, you would, right? Can you graph the equation that you already made on the front side? What is Y in terms of X? Guys, for example, here, I'll really help you guys out. Guys, what if X is equal to 0? Does that mean you didn't fold up the side at all?
Yeah.
If X is equal to 0, what does Y have to be equal to? 12. Right, it'd be the full 12. Isn't that has to be a point on the graph, doesn't it? Right. And you guys also told me that the maximum you could fold X would be how much? 6, right? Which would not even be reasonable because by the time you fold it to 6, what is Y equal to? 0. You don't have any height left. Okay. Oh, that looks like Y. Can you guys figure out what the rest of that graph looks like? And of course, the equation on the front could match that graph. Okay. Now, this graph right here. What's the maximum buoyant force? Like how much weight could you basically put in it? How much cargo can you carry? As a function of how much you fold up the side X, right? Like, if you don't fold up X at all, you just have a flat sheet. How much weight can that carry? Yeah, none. Ooh, that sounds like a point on the graph, right? But if you fold X all the way to 6 centimeters, now you're back to just no volume anymore, which is going to be how much weight can you carry? Also none. Huh. Do you guys think this is going to be some kind of upside down looking curve?
Yeah.
Right. Now, I'm not going to say it's a parabola because I don't think it's a parabola, but it's going to be some kind of upside down looking curve like this. You guys see that? Okay. Right. Oh, and I'll help you out with some dimensional analysis here too to convert cubic centimeters to cubic meters. That could be helpful, maybe. Okay. Right, you guys good? All right. Yeah, because I did kind of mix and match units here. I have centimeters here versus newtons here. Maybe I shouldn't end that, but like that. Okay. One last detail I want to point out. Do you guys see this detail in the italics that says calculus students use calculus to optimize the dimensions of the boat box? Right, you guys see that? Right. Oh, I think about half you guys are in calculus. You guys have probably done optimization by now, right? If you're in calculus, you've done optimization. Right. So let me review with you guys just the broad concept. Playing off this graph here. Because this graph, okay, what is the well, I put the maximum buoyant force as a function of how much you fold up side. This could be in newtons, this could be at meters per centimeters. Okay. Now, I bet your graph is gonna look something like this. Okay. Now, again, I'm saying it's not necessarily a parabola, it might not be exactly that shape, but maybe you could plot a bunch of points. Right? Some kind of upside down curve. Right? Where if you don't fold it up at all, you don't get any volume. And if you fold it all the way 6 centimeters, you don't get any volume. But somewhere in the middle is going to open up a box. Right? And you want to maximize. Right? Now, the calculus version of optimization has to do with rates of change. Because if I hold my ruler flush to the curve and I go around and looking at the slope of this all the way around, what is the slope at the peak of that upside down curve? Zero slope, right? So you guys know, if you go through calculus, if you take a rate change equation called the derivative, you set that equal to 0, that'll tell you exactly, bam, where that is, right? So if you set up an equation for the volume in terms of x, I bet you could do a little calculus to get the answer, right? But if you're not calculus, again, half you guys aren't, that's okay. Because you guys can do this empirically. You guys can just hold a bunch of different shaped boat boxes, put different weights in them, and see what floats. Okay, right. You guys think you can figure that out? All right.